You know the drill. If there's ever any technical issues or anything, just let me know. Welcome to Steel Design. This class is my baby. I mean, this is definitely the you know, I don't want to say the other classes aren't my passion, but this is what my area of expertise is, and so I really love steel design. I'm really excited to teach it. It's definitely a different pace and a different it's a different experience than structural analysis, but it's a lot of fun, and I think you'll really like it. I'm going to go over some logistics today, but if you wanted a TLDR or whatnot, or a very abbreviated summary, if you had me last semester for structural analysis, this course is going to run very much the same way in terms of the class operation, the procedure. And if you had me for concrete design last spring when we went online during lockdown due to COVID, it's going to operate very much like that. The lectures are going to be very topic-based and focus-based. You're going to have a short assignment due every lecture, you know, very similar. But let's get into it and get through the process. First off, the technology tools. So Blackboard in here is going to be our primary tool of the content delivery for the class. We're going to meet every day at our scheduled class time here. I know that's a little different from those of you that are in Capstone because we're using Teams a lot in there, but this is just while it is a very fun and very applied class, it is a class. So we're going to do collaborate meetings here. I'll post all the grades to Blackboard, all the notes, the homework assignments. The exams will be conducted via Blackboard. In fact, I've done a lot of work over break to sort of set up everything for this class, and it's already pretty much set up, ready to go, all the guts of the course shell. So it hopefully should be a lot easier from an implementation standpoint. I sort of learned my lessons from last semester. You are going to be scanning and turning in homework assignments, much like you've done in structural analysis and concrete design last spring, and in a lot of your other classes. So, I recommend Cam Scanner. You know, if you have a smartphone, you can just take a picture and scan it, send it out. You can use whatever app you want, but I find it to be pretty easy. And again, if you sign up with an EDU email address, it removes the watermark at the bottom, and you get a couple other features. So there you go. Let's talk about Teams. So Teams is going to be sort of our backup for live lectures in case Blackboard decides to poop out on us. I'll do some periodic announcements through the class channel. And I want to mention something else on Teams right now. So earlier in the winter break, I posted a poll on Teams for the manual. I'm going to remind everybody about that right now. If you have your manual, let me know on the Teams channel, please. And if you're still waiting on it, just hold off. If you have yet to purchase your manual, do it now because we're going to start using it pretty quickly, and we'll be using it pretty regularly. I've got some resources on Blackboard that I'm going to show you here in a bit that will make your life a little easier, but you do need it pretty soon. So yeah. Let me talk about the grade and let me talk about the class. So first off, the grade structure is very similar to the other grades that or the structures that I've had in other classes. The one thing I'll mention is the exams. So usually I have 20% finals on all my exams. This class is a little different. So if you notice, exam 2 is only worth 15% and exam 3 is worth 25%. There's a reason for that. This class, more than probably any other that I teach, is very modular. One of the things that I've said in other classes is that I don't like to have material bleed over from one exam to another. Well, in here, this is probably the most modular of courses that I teach. And the second exam covers connections. It covers bolted connections and welded connections. And what you'll find is that of all the topics we cover in this class, those two are the easiest. And so that exam, there just isn't a lot on it, but columns and beams, which is what the final is on, has a little bit more. So it made a little bit more sense to make that exam a little bigger and exam 2 a little smaller. Yes, sir.
So each exam, so the final exam is not going to be comprehensive. It's just tentative.
No. It's what? It's not comprehensive. It's not comprehensive. Exam 1 covers the introductory material, and then our first main topic, which is tension members. Exam 2 covers bolted and welded connections. Exam 3 covers columns and beams. So they're not comprehensive. And other than some of my other classes, there's very little material that bleeds over from one exam to another. Now, one thing I do want to mention is the textbook for the class. So there isn't a textbook for the class. All of the homeworks and the exams are custom made. I make them myself, all the problems, everything. But you do need the manual. Now, one of the things I'll also say about the manual, so this is my manual, and if you notice, I'll sort of put this up on the camera. You can see a bunch of tabs and whatnot that I have in the manual that are sort of bookmarks for certain things that that are pretty important throughout the semester. It would probably be a good idea to run down to Office Depot and get you some Post-it notes or something, some labels to sort of indicate this, because there are some guides that we're going to use very regularly throughout the semester. Some of these tables, like for instance, this is the table that we use to determine capacities of bolts in shear, and this is like we'll be using this a lot. And instead of having to find it every time, I mean, you can see my little tab. I'll put it on the little camera, but I actually have a little symbol there of a bolt, and oh, there's the bolts. So it's probably not a bad idea to have some tabs there. As the semester progresses, I'll sort of indicate, yes, there is. Now, I'll show you the homework schedule here in a bit, but some of them will probably be really short assignments. Like we have one where we do shear lag factors, and it probably takes about, I don't know, 10 minutes max. So, but yeah, we will have the daily homework assignments just because of the nature of the topics that we cover. Let me go back to the notes. Okay, a couple things. So I am going to take attendance using the tool on Blackboard, so I know who's logged into the session and how long they've logged in. And I also know, you know, like I'll know who logged in, how long you logged in, when you logged in. So I use that. It's the same thing I did last semester, so there's not really anything worth mentioning there. But you know how I am. I'm pretty easy to get along with. If you've got technical issues or glitches or anything, just let me know. I'm easy to get along with there. This class, I know we mentioned in Capstone how I may record some, but not everything. And here, I'm going to record and post everything. It's going to be a lot like structural analysis. So I've already got a link on Blackboard for the YouTube playlist, and it'll be like I did last semester. I'll record the video, post it to Blackboard, and you know it'll be the same. They might not be immediately posted, but you should be able to download the recordings as well on Blackboard. So as soon as they're available, you'll have access to them. Well, it's funny, I guess, isn't YouTube starting to do that without my permission? Or, I mean, they're starting to sort of do that anyways. So I've always kept ads off of my videos, but just get an ad blocker. Yeah, I've always kept ads off. I just haven't messed with it. The homeworks, it's going to be the same homework structure that we've done in the past, and there's so many homework assignments, but they're so short that what I found is that, you know, most students they either get them in on time or they're late, or you know, basically, long story short is if I've already assigned the grades and I don't have your homework, it'll be a 0. But there are so many that any one homework assignment doesn't. If you miss any one homework assignment, it's not that big of a deal. Hold on, I saw a comment there. What was that? If you hate ads, teachers record lecture through Collaborate. I guess that fits with me. Exams. So those of you that had me for structures last semester, the exams are like the same. It'll be the same format, same process. Those of you that didn't, so the exam method that I developed last semester was sort of born out of the trial by fire that we had last spring when we, went suddenly on the lockdown. And so whenever we have an exam, there will be two things that pop up on Blackboard. The first will actually be the timed exam, and the second will be a means for you to upload your scratch calcs. And so we'll have a timed exam, and then the scratch calcs you'll be able to upload a little bit after. I do the same process where, if it's an hour-long exam, I design it so that I can complete it in 20 minutes. Rule of three. I've never the timing issues have never really been a major issue on the exams in this class. There's never really been, instances where the students have felt rushed. Maybe on exam 1, but not really on 2 and 3, especially with 3 because it's the final and it's not written to be any longer than any of the others. So, and 2 is just the bolted connection stuff is really short. So, let me show you the course schedule. So here's the course schedule, and this is in the syllabus, so it's not like, if there's anything that you're having trouble reading, you can zoom in on the syllabus. So I want to highlight a couple of things. So first off, let me talk about when the exams are and why they are when they are. This class is very modular, okay? So when we cover, let's say, tension members, you can see there's like 9 lectures on tension members. We're going to have an exam right after that because the material's fresh in your head. Let's have the exam. Let's move on. And so I assigned the exams right when we finished a topic. Now, one that was a little tough that I'll admit I didn't like organizing the exams this way, but I really didn't have a choice the way the semester worked out, is the second exam. We're going to have our exam review. We're going to have the spring holiday, and then we're going to have our exam on Monday when we come back on bolts and welds. But fortunately, and as you'll understand as we start covering the topic, bolts and welds are not the most difficult thing. So I don't think that's going to be too bad. We have our final on Tuesday of finals week from 10:15 to 12:15 on columns and beams. And so the other two things that I'll point out is that, again, like I've done in previous classes, before the exam, there is a scheduled exam review date where I'll spend a couple minutes talking about what's going to be on the exam and then open the floor for questions. The final thing I will mention is what's going on Monday, February 22nd. I mentioned something, and I don't think it was during structural analysis. I think it might have been during my senior seminar course where I said, it went back to that mental health day that we had last semester. Admittedly, I wasn't really a fan of how that was implemented because it was, in the middle of the semester, it was last minute. I went through the lecture schedule, and based on the topics that were being covered, I think I'm able to squeeze in a day where we can take it off. I say I think I can. I'm not saying I know I can. So I want to be clear when I say this is tentative, but tentatively, we'll take that Monday off and just take it off. Take a break, come back recharged, ready for bolted connections. So it's tentative, but I'm going to give it a shot. Any questions? Okay. Oh, I do have one other thing I want to mention. So, like I said about the manual, I really want you to try and get your manual in as fast as possible. If you haven't already purchased it, you really should do so soon. But if you can't, if for some reason you're going to have an issue there, let me stop the share here. Okay, so this is Blackboard, and this is what you should see when you log into Blackboard. If you go to lecture notes and supplements, if it'll open, I said, okay, here we go. What you see right now are, you see course overview, and there's this thing called AISC resources, okay? So AISC stands for the American Institute of Steel Construction. They write this little manual I have in my hands. Now, when you buy the manual, what you're buying, and we'll talk about the manual next week in more detail, but what you're buying are a lot of the design aids and design tools that are in the middle of the manual. But there are a couple of things that are in this manual that you can download for free. Not the bulk of it, but a couple things that'll help out through some homework assignments. The first is the actual specification, and I'll show you where that is in the manual here in a second. But the specification is basically this document that illustrates how we design structures, in the United States. So if I go, past the table of contents, all this. So just a little bit about the specification. So you'll see there are a series of chapters, and the chapters are organized by letter. So this is chapter A. This is, chapter B. You can see chapter B is general design requirements. And as you fast forward through the manual, let me go past this a little bit. Okay, so this is chapter D. Chapter D is the design of members for tension. This is going to be one of the first sections of the manual that we use pretty heavily when we design tension members, right? And so this is the chapter on tension members. Chapter E is the design of members for compression. So this is what you use to design columns. Chapter F is what you use to design beams. This is designed for flexure. Chapter J is the J on connections. And everything that you're seeing on the screen here is actually in the manual proper, and I'll show you where it is here in a second. But for those of you that are still waiting on your manual, this is here. The other thing that you'll find on Blackboard is this Excel sheet. Okay, now this Excel sheet, when you download it, you'll see this sort of README file, and if you look on the bottom where it says database v15.0, I know this looks like a mess, but basically this is all the dimensions and the sizes of all of the rolled shapes that we use, W sections, angles, channels, what have you. And so if you're still waiting on your manual, you can use this. I would really like you to get to a point where you can start using your manual, but this is sort of like last resort stuff if you're still waiting on it. So yeah, let me stop this share here, and I'll show you something. Does anybody have their manual with them in their hands right now?
I have it like 5 feet away.
All right, so I'll show you something real quick. Okay, so that document where it said specification, okay, if you look on these pages right here, you should see these like little black tabs, right? And they have abbreviations in front of them. They have like beam, column, tension member, bolts, welds. There's a tab that says SPEC called spec. It's near the back of the manual, kind of like back here. This is the section that actually contains the specification. So if you start flipping through these pages a bit, you'll start to see the, Chapter D, design of members for tension, Chapter E, design of members for compression. And so we'll review this part of the manual in some pretty significant detail. This part of the manual is also available for download there on Blackboard. Another thing that's worth mentioning, and I'll go in this in more detail, but you can tell you're in the right part of the manual because next to it, you see these pages that are lined in gray?
Yeah.
See these? Okay, so anytime that you're dealing with structural design specifications, be it steel design, concrete design, bridge engineering, it doesn't matter. Even in other disciplines like transportation or what have you. Their standards and specifications tend to be written in two components. There's the code, and then there's the commentary. And so the code will say, this is what you as the engineer will do, and the commentary will explain why you're doing it. Sometimes they're written side by side, but in the steel manual land, the commentary are these gray pages. So just point of fact in the future, if you're ever trying to understand why you're doing something, the commentary tends to explain why, and it also tends to cite all of the research that goes into that discussion. Mr. Adkins.
Now, this is like when we're as an actual engineer and we get a new edition out. Should we keep the older editions as a reference or not? Because if we have to look at a structure from that was built during this time period per se. Never mind.
That's my answer.
All the
I have
engineers
a
I
few.
worked for had those nice bookshelves full of
I have a few of them, yeah. One of the interesting things about the manuals, and we'll talk about this more on Friday, but there are actually two different design philosophies that we can use for designing structures. One of them is called allowable stress design, and one of them is called load and resistance factor design. And the steel industry used to put out different sets of manuals for different philosophies. So there were 9 editions of the ASD manual, and there were 3 editions of the LRFD. LRFD was a bit newer. So when they got ready to publish a new manual, they said, well, we've got 9 manuals here and 3 manuals here. So we published 12 manuals. So what they did is come up with the 13th edition that was just both of those philosophies together. And so then came the 14th and now the 15th edition. When you flip through the manual, you'll notice a lot of sheets that are colored like green and blue. Green refers to ASD and blue refers to LRFD. We're going to be using the blue numbers throughout the semester, but I'll explain what is ASD and what is LRFD on Friday. It's some pretty cool stuff. Let me go back to the spreadsheet or to the presentation. Okay. Any other questions before I try and start to introduce just what the heck it is we're doing in this class?
I'm trying to think how. So on the homework, do we want to reference what tables we use as a reference point on there or not?
You will, but I'll say this, because of the daily homework assignments that we're doing, those references will be a bit easier on you. In other words, because the homework is broken up, like you aren't going to have, too many homework assignments where you're having to reference a bunch of stuff. And some homeworks will be focused on a particular guide, like use this table to do this. So you won't really need to reference it because I'll know what table you're using. But that'll become clear as we move forward. But the short answer is yes, you'll want to at least provide some reference as to where you're getting values. But don't worry, if this book scares you, it will scare you a lot less in the coming weeks. It's not that bad. And I think I do a reasonable job of making it less scary. Some of you are going to hold me to that, I know. Okay, let's talk about structural design. One of the things I'll definitely emphasize is that this class is different in spirit and nature from structural analysis. Structural analysis was a very theory-driven, mathematical puzzle type class. Here's a truss, here's these loads with arrows on it, and the arrows represent 20 kips. What's the force in this member, and so on and so forth. It is a very relevant science, but there was some theory, ideas behind it. This is a very practical applications-based course. But I want to kind of understand, I want you to understand where what we did last semester fits into the big picture. And it might seem like a weird way to start after you've already taken structural analysis, but maybe we should talk about just what the heck structural engineering even is. Structural engineering is, you could look up some Wikipedia or dictionary-based definition, but essentially it's the science and art of designing structures so that they can safely resist the forces to which they may be subjected. That's structural engineering. And we tend to really focus on 2 things, buildings and bridges. And in this course, most of what we do tends to focus on buildings because we tend to treat the loads as stationary, as static. One thing you'll find when you open up the bridge design specification is a lot of the codes and provisions in the bridge spec that are related to steel are very similar. So it's not like, if you start designing steel bridges after you've learned this class that it's completely different, because it's not. A lot of the theory is very transferable. But what I want you to start thinking about in terms of structural engineering, I want you to start thinking on 2 sides of the equation. I want you to start thinking about loads and resistance, okay? So loads are what the structure must hold up. And then the resistance is how strong the structure is. So let's take an example from what we did last semester. Let's talk about a truss. Okay, so here's a truss. It's got, you know, some forces on it. So what do? You know, use statics to solve for the reactions, and then you might say method of joints. You might start working your way down the truss. And let's take a look at a given truss member. Let's say that truss member is going to experience 320 kips in tension. Okay, so that truss member has 320 kips in tension. That's the loads. The next thing I've got to do, and then that's where structural analysis stopped. I just said, tell me what the force in that truss member is. And so that would be the load side. That member is experiencing 320 kips in tension. What we're going to do in this class is we're going to take it a step further and say that member is experiencing 320 kips in tension. Now I need to select a member that can safely resist that load. So I've got this truss member. It needs to be a W10 by 49 with 3/4 inch diameter bolts, spaced 3 inches apart. That's going to be our role in here, is to select a member to safely resist that load. And in short, the role of a structural engineer is to select those members such that the resistances are greater than or equal to the loads. As long as your structure is strong enough to hold up the loads it's subjected to, your structure is safe. Okay, and unfortunately that brings up a little bit of a problem, because if I'm designing a bridge out in Huntington and I know that my grandma is going to be driving over that bridge every day to get groceries or go to the post office, and I'm thinking, well, gosh, I don't want anything to happen to grandma, I'm going to design that bridge massively. I'm going to use super huge beams and super huge elements because I don't want anything to happen to grandma. I want that bridge to not fail at all. But what's the problem with that bridge if I use super huge beams and super huge elements? What's the problem with it?
Those super huge beams are more expensive.
It's too expensive. Exactly right. So engineers, and I say this about structural engineers, but it's really true about engineers in general, is that we tend to walk a tightrope between safety and economy. And that's where this comes into play. A lot of the specifications that we have, that you know, we need a means of accurately determining the strength of a section. We need to understand the mechanics of a beam so that we understand its strength, and then we pick a section that is safe but also economical. Because, and we always have to ensure safety. You know, the welfare of the public is obviously our foremost concern. But once we've met that, the structure that we design has to be economical and competitive and cost effective. Mr. Adkins.
As I understand it, you understand that, but the matter of saving money and safety can be so conflicted. You can't always balance it out, and even safety must be taken paramount above all else.
That's true. That's true. But there's a couple other things you have to consider. First off, a lot of times, I'm going to try and choose my words carefully here. If you don't feel competent or qualified in the structure that you're designing, you shouldn't be designing it. All right. And what I try and combat is I don't want any of my students leaving my class working on projects that they're not trained for. If you don't feel competent in the field that you're in, the structure that you're designing, you shouldn't be designing it. So that's number one. Number two is that, you know, the specification is designed to ensure that failure doesn't happen. And if you're following it and you understand how it works, then you should be fine. The gross negligent cases of structural failure tend to happen when people don't follow the spec or don't follow the process. So yeah, and we're actually going to talk about some of these cases, you know, like the Kansas City Hyatt Regency, the walkway failure, where you know 100 people died. We're going to talk about that later on in the semester and what went wrong. And what went wrong wasn't a failure of the specification. It wasn't a failure of mechanics or materials. It was a human failure. It was a failure of communication. It was a failure of following the process. You're right. And that's fair. And I think what Mr. Blizzard said in the chat was a very good way of putting it. And what I'm going to show you is not just the art, but the science behind that. because there are some processes that you can follow that will ensure you'll find the lightest but the most efficient section that's safe. One of the things that I want to do today, and it's a term that we're going to pick up on Friday, and it is a term that is going to be very relevant to what we do throughout this semester, is the concept of a limit state. I'm going to throw that term out a lot throughout this semester. So what is a limit state? A limit state is a condition of a structure beyond which it no longer fulfills the relevant design criteria. A simple example of that would just be like failure of a component. So I have, let's say, a column, right? So here, let me stop the share here for a second. So I have a column, right? Here's my little, rubber I-beam column. Okay, so I have a column, okay, and I apply load to that column. Okay, now if I keep increasing this load, what's going to happen to this column? Somebody tell me.
It will either begin to compress or begin to bend.
Yes. Okay. So, and we have a name for that sudden compressive failure, and we call it buckling. Okay. Now, the way you said that was excellent, because what you did just there is you defined two limit states. You defined failure under general compressive stress, which we might have to ask ourselves, okay, what would be the limit? Maybe the limit is when the metal reaches its yield stress. Okay, so compressive yielding, that would be a limit state. And another limit state might be compressive buckling. Here's the column, bam, it buckles. Okay, so for each of those limit states, I might compute a capacity. What is the capacity of this element such that it reaches its limit before it buckles? Or what is the capacity of this element before it reaches its capacity under yielding, right? And so I've got these two. Now for this element, I would argue that its buckling capacity is probably lower than its capacity under just yielding. But that might change if the column was, instead of being this long, what if the column was this long? What if it was a really short column? Maybe that really short column wouldn't buckle. Maybe it would just, flatten out like just like it would just, fail in compression. It would just squash. So for each of those, I would compute a capacity. Those would be my two limit states. And as long as the load I'm putting on it is less than the capacity under those two limit states, then I would say it was fine. But as soon as the load exceeds those values, I have violated my limit state. Now, there are a few different limit states that are types of limit states that we deal with as structural engineers. Generally, we tend to deal with two types of limit states. One is what we call a strength limit state, or strength limit states are the ones that are sort of related to safety. So those are kind of the ones that we were talking about just now with the rubber I-beam. It could either buckle or it could fail in compression. So that tends to be what we mean by a strength limit state. And most of this semester is going to be focused on looking at strength limit states. However, there's a whole assortment of other types of limit states that we have to design for. One of them is just deflection. If a beam deflects too much and it deflects elastically, in no way, shape, or form does that mean it's going to fail and fall down and kill somebody, right? A beam can deflect a fair amount and still not fail, but that doesn't mean we want that to happen, right? So, for instance, if you've ever, all right, let me ask a question. How many of you have ever been in either a house or a building that had plaster roofs, like plaster on the roof?
I'm unsure.
I'm sure there's a fair amount of you that have. Okay, so the beams, yeah, the ceiling, the plaster on the ceiling, yeah. So the beams that support those roof structures, those beams are designed to have a maximum deflection of L/360. Okay, so we take the length of the beam, we divide it by 360, and we say that's the maximum deflection. Now, if the beam, let's say it's a wooden, joist. If that wooden joist deflects more than L/360, it does not mean that the beam is going to fall down and kill somebody. That's not what that means. What it means is where did that L over 360 come from? If the beam deflects more than L over 360, you'll start to crack the plaster. Now, that doesn't mean that again, it's not a matter of safety, but we're getting to a point where if it deflects more than L over 360, it starts to, not meet its day-to-day performance expectations. And so we call those serviceability limit states. So serviceability limit states are ones that are not related to failure, but more about day-to-day performance of the structure. So if you have a structure that vibrates too much, or if you have a structure that deflects too much, it might not fail, but it's not doing what we want it to do. Mr. Adkins.
Now, as I recall, in all kinds of structures, we're aiming for an average value, not a extreme amount. But as I understand it, if we go to an extreme at one point, like one day, that's all right. It'll survive. But
well,
go ahead.
No. You go ahead.
Well, I'm assuming we check the structure every once in a while to make sure it's all right, per se, as well.
So I'll say a couple things about that. We actually typically design for worst case scenarios. So I don't want to get too far into tomorrow's lecture, because Friday's lecture is actually going to explicitly cover some of the stuff that you're talking about. But to sort of cover it a little bit, what I'll say is this. Number one of the big things that we have to handle is the concept of uncertainty. Okay, so let's take my office. Okay, let's take the floor beams that I'm standing on right now. Okay, these floor beams that are holding up this floor are holding up two different types of loads. One are dead loads being the weight of the beam, the weight of the slab, the weight of the carpet, the mechanical, the electrical, the plumbing, all that, the permanent loads. We call those dead loads. It's also holding up live loads. Live loads are related to occupancy, what the office is being used for. So me, the office furniture, so on and so forth. Now, when I'm a structural engineer does this, I have no idea. Whoa, that had some echo there. I have no idea what the, who this Dr. Michelson guy is and what he's going to have in his office. I have much more uncertainty associated with those occupancy loads than I do the dead loads. I mean, if I know that concrete weighs X number of pounds per cubic foot, and I know the slab's going to be so many inches thick, I can compute the weight of the slab, and I can compute the weight of the beam and the weight of the carpet and all of that. I have much more certainty about the dead loads than I do the live loads. So when I start applying load factors, you'll see how in some of our load combinations, the load factors associated with the live loads are higher. We do that because we have more uncertainty associated with the live loads. That concept will be a little bit more clear on Friday, and it goes into the different design philosophies that we can use. One of them you're very familiar with, which is just to use a blanket factor of safety. Like, here's the capacity, let's just divide it by 2. And the other is a more refined one called LRFD, which is what we'll use throughout the semester. But to hopefully that's sort of addressed your response. Again, I think we'll cover it a bit more on Friday. I do want to mention a couple of other things. There are some other objectives that we need to consider when designing structures. And admittedly, we're not going to talk about a lot of this stuff directly, but I do kind of want to mention it. Number one, structural engineers are not they don't answer to no one. Like they're not entities without bosses. They do serve a client. They do serve a purpose in a given project. So there are some things you need to consider. Number one is the aesthetics. The structural engineer has to work with the client or the architect to ensure that the structure meets the needs of the project. I mean, if structural engineers had their way, we would design nice, pretty boxes. Like, our buildings would just be a box, with evenly spaced columns and beams, and we would design the structure in a day. but that's a boring building, if we're being honest. I mean, very rarely do you find a building out there that's just a box. You know, there is the needs of the client, the needs of the architect. I mean, just take the engineering building here at Marshall. It's not a box, it's a complex building. And so the structural engineer has to work with the architect in order to ensure that the skeleton that holds the building up, you know, makes sense. I mean, it really wouldn't make sense if I had a column right here in the middle of my office. You know, you could see in my office how there's a column right here behind this you know, a portion where it comes out, but that's not getting in the way of me, you know, conducting business in my office. That's fine. So you have to work with the architect to ensure that the structure, you know, comports with the overall vision. You also have to ensure that the building is constructible. So many times in you know, when you first start learning about structural engineering as a student, you tend to think about what the structure looks like when it's complete. But you also have to ensure that the structure can survive the construction process. So like a real world example, if you take some of the curved box girder bridges that serve as like the overpass interchanges, like in Charleston, you know, where like 64 and 77 and 79, all that interchange happens. Some of those structures, their worst case stress state is not now when the structure is complete, but it was actually during construction when it had 8 inches of wet concrete on it and the concrete wasn't composite with the deck. So it's one of those instances where if it survives construction, it'll survive its design life. So you have to understand that process. And does the resulting design present excess construction challenges? Like, yeah, the structure's great, but now, you know, the pieces that you picked are going to take 12 weeks to deliver as opposed to 4 weeks, you know, stuff like that. Is it economically competitive? You got to kind of think about these things. These 2 graphs on this slide, if the well, give me 1 sec. Let me just say this, and then I'll entertain your question. These 2 graphs really sort of illustrate your impact on a structural design project. The ability to influence the cost of a project over time is greatly diminished as the project goes on. So, you know, if you're at the beginning conceptual planning stages of a project, the decisions you make have a big influence of the cost of that project. But by the time the project is started up, the costs are what they are. So those decisions that you make at the beginning are incredibly important. But on the flip side, what if you need to change something? Well, it doesn't cost a lot of money to change your mind at the conceptual planning phase. But if you're putting the roof on the building and you find out that there's something wrong with the first floor, that's going to cost some money. So it's just something to keep in mind as you work through a project. Mr. Adkins.
On the previous slide, it was about aesthetics, constructability, and economy. On those 3 point objectives, the last 2, constructability and economy, are the more higher priority than aesthetics.
Not necessarily. Not necessarily. If you're designing a building, I'm not. It's change orders. There you go. It's not. Let me say this. I think we would think that, but if we're talking about, let's take the engineering building. Okay, we would think that constructability and economy is important, and yes, it's true. But let's take the engineering building. The cost of the structure, the steel skeleton, the concrete slabs that holds this building up, is probably about 15 to maybe 15%, maybe 20% on a bad day of the cost of the entire building. I mean, because there's mechanical, electrical, plumbing, carpet, painting, drywall, you know, the IT that needed to go in the building, the parking, the grounds, the purchasing of the land. The structure is just a piece of the building. It's not the big picture. Now, it is different in Bridgeland. In Bridgeland, the structure is like the entire cost of the project. So also in Bridgeland, the engineer tends to have a bit more control when, you know, your client is the DOT. the DOT has engineers working for them, so you're working one-on-one with engineers. Whereas if it's the building side of things, your client tends to be the architect, and the architect tends to work with the owner, and the owner, they're not engineers. So it's a different dynamic.
Okay, I guess some more sense to it.
Yeah. Are there any common issues when working with architects or clients as far as the design process goes? I would say that there's and we'll probably have to close on this question because of time, but I'd say that the one issue that tends to arise is architects tend to love open spaces, open concept. If an architect had their way, they would have columns 100 feet on center and completely open space to do whatever they want inside the building. And some of that is to meet the needs of the client, and some of that is in the freedom to meet the needs of their client. But the structural engineer has to come in and say, okay, that's actually not possible. Like physics won't let you proportion the building that way, because if you do, it will fall down and kill somebody. So there's some give and take. Now, in fairness, most structural engineers are at least trained, or I'm sorry, most architects are at least trained in some of the basics of structural engineering, so that they understand what you're talking about. Doesn't mean they have to be experts in it, but they at least get what you're trying to do. There's some give and take there that has to be done. We possess a challenge just as architects possess a challenge. An architect has to take the vision of a client who doesn't know anything about engineering and turn it into real life, and we have to make that vision safe. So, you kind of, I mean, there's always a running joke that architects and engineers don't get along, but really, like, they have to work together to make an abstract idea a reality. So it's definitely a challenge, but it's a rewarding one. Any other quick questions before we call it? We don't have any homework assignments today, so don't worry about that. Yeah, I mean, in all honesty, we're all trying to achieve the same goal. And they have challenges that, quite frankly, I don't think I'd be good at. I don't know that I could take this abstract idea from a client and turn it into a vision. Like, it's just, I'm not artistic like that. I know where my skills are. I highly respect architects that can do that. So.
Yeah, I gotta say that last slide is just really true, like just fundamentally true, based on, like, I ran projects in post-tensioning and it was like that. It was exactly like that. The later you wanted something much more expensive, it got.
Yep, that's true. All right, we're at 11:51. I'm gonna have to call it. Tomorrow, or on Friday, we're actually gonna discuss the design philosophy that we use and try and explain it. And then next week we start diving into this thing. Don't forget the poll on Teams. If you haven't already responded to that, and you have your manual, please do. And with that, I'm gonna stop the recording, and we will see you all on Friday.
Hey, Dr. Michelson.
Yes.
Can you stay for just a second for a quick question related to something else?
Sure. Let me stop the recording.